So just as a warm-up, we want to look at this first problem here. This was the technique of what, folks? If we were going to find dy dx, what do we need to use? What technique?
Implicit differentiation.
Yeah, we use that technique of implicit differentiation. And this is a really nice skill to develop because a lot of things are difficult to solve. Like I think in this case, you'd have to complete the square if you wanted to solve for y. But if I put a cube on there or even a 6th degree, it may be difficult or even impossible to solve for y explicitly. And so this tool of implicit differentiation is exceptionally handy. So how does it work? Well, we take our function, x plus y, or our equation, excuse me. And again, we're thinking of y as an implicit function of x, and we just take d dx of both sides. Okay. So when we do so, let's see here, we're going to get 1 plus, I'll go ahead and write 1y prime just to emphasize how these really are the same step, but normally we just write y prime there. And on the right-hand side, we'd have 2x plus 2y y prime. So could I get a reaction from you? How are we doing with that? Thank you, thank you. Thumbs up. Great. That works. Whatever you want to do. Okay. Thank you, folks. So now what do we do? Well, here I have kind of two options. Notice I didn't ask you to find dy dx. Since I didn't ask you to find dy dx, what could you do right off the get-go? You could go ahead and plug in 0 for x and 1 for y right now, and then solve for dy dx. So we could go ahead and do that, and so I'll do that here. So we'll have 1 plus y prime is equal to 2 times 0 plus 2 times 1 times y prime. And when we clean everything up there, we get 1 plus y prime is equal to y prime. Oops, we would have had a problem there. Is equal to 2y prime. Okay? And if I subtract over that y prime, I get 1 is equal to y prime. So we would say that dy dx, evaluated at 0, 1, is just 1. Okay? That's option 1. Notice that I never actually solved for y prime. Do I have a mistake here? Somebody saying so? Nope. Okay. Feel free to jump in there, folks. I usually make more mistakes than you do before breakfast. All right. What's option 2, though? Option 2 is kind of more typically what you've done in these problems, where we solve this equation for y prime. So we're going to take 1 plus y prime is equal to 2x plus 2y y prime. We're going to solve for y prime. So let's see here. I think I'd like to subtract over. So we'll have y prime minus 2y y prime is equal to 2x minus 1. Folks, could you take all the y prime terms over the right-hand side? Certainly. If you do, your answer will look slightly different than mine. But it will be correct if you don't make a mistake. Folks, what do I do now? What's my next step here, folks?
You take out the y prime.
We can factor out a y prime. Very good. So if we factor out a y prime, we get 1 minus 2y times the quantity y prime is equal to 2x minus 1. And so at long last, we find that y prime is equal to 2x minus 1 all over 1 minus 2y. Now we can go ahead and evaluate this. We could evaluate y prime when x is 0 and y is 1. But notice in this case, we still end up with 1. So you could do this problem either way. And I'm showing you that because if I were asking you to find y prime, you'd have to do option 2, right? If the question said find y prime, you have to isolate that y prime term. But if all you're doing is looking for the derivative at a point, it may be easier to do option 1, especially if you've got some zeros. It might clean up a whole bunch of stuff before you do any algebra. And so that could make the algebra far easier, that option 1. Any questions on that, folks? Thank you for the reactions. I got a couple there. Any questions? So the next one I want to look at is number 2. And this is a what type of problem, folks? One thing you should practice doing is classifying these problems. Try to think like a teacher and say, if I were going to describe this problem to a student, what would I call this type of problem? So this came from our last section. What did we call this? Go ahead, Shane.
Related rates problem.
This is a related rates problem. We have multiple variables. In this case, we've got area, and we've got base, and we've got height. We've got multiple variables, and some of them we're told how they're changing, and then we're asked to find how the other one, the missing one, is changing. Okay. So how do your related rates problems go? I'd like everyone to go ahead and give this a shot, and then we'll talk. Okay, folks, I know that wasn't necessarily quite enough time for you to get through everything, but let's go ahead and give it a shot. Miles, that looks good. Yep, you got the right answer there. So what we need here is a formula that relates all of the important variables together, or the pertinent variables together. So I think in this case, it's the area formula for a triangle. Okay. Also, that looks good. So folks, we've got area, base, and height, and what's a formula that would tie those together? Now, if there's another formula that you can think of, you're welcome to use it. You don't have to use this one, but I can't think of another one off the top of my head. Okay? So, now we're going to go ahead and do what? This is the key calculus step, where we take d dt of both sides. This is the related rates step, where we say, if the formula has to hold, then the derivative of each side of the formula has to also hold. If area is equal to 1/2 base times height, then the derivative of the area needs to be equal to the derivative of the right-hand side. And here we think of taking it with respect to time. Okay. So that gives us that dA dt is equal to 1/2 b dH dt. I'm applying my product rule here, right? Plus h times 1/2 dB dt. Now folks, please, we've got the letters A, B, and H here, but I could make these formulas could be far more complicated, and you're using the same implicit differentiation technique that we did in number 1 here. This isn't some sort of new technique. The only difference is we're taking the derivative with respect to time instead of x. We're asking, as time changes, how does the area change? And we're asking, as time changes, how does the product of b and h and 1/2, how does that change? Okay. So again, the picture that maybe would go with this is here we've got some triangle, and it's got a base, and the triangle has some sort of height, and the height is increasing and the base is increasing, and we're asking the question, what's happening to the area of this triangle as those both change with time? So folks, I can't illustrate this very well. I can't illustrate it in a one drawing because the drawing would be changing as time progresses. Now, the way we then do this is this part is always true. This is our related rates formula. This part's always true. But now I'm going to ask you about a snapshot in time. So imagine you could watch an animation of the base getting bigger and the height getting bigger. But then at some point I'm going to take a picture. When am I going to take a picture? I'm going to take a picture when the base is 20 and the height is 18. I'm going to take a picture of this problem. And then ask, at that instant, how quickly is the area changing? Okay. So here we go. We've got that A prime is equal to 1/2. Now, folks, here I've got something about the base. It says the base and it says this. And then I've got something about the base and it says this. Which of those two, 20 or 4, am I going to substitute in for B? Pause for a second. Don't say it out loud just yet. Which of those two am I going to plug in for B? The answer is 20. I'm talking about the base in this specific instance in time when I've taken this snapshot. Okay. I couldn't plug in a 20 for B earlier because as this, for different instances of time, this base is a different size. Okay. But then I'm going to multiply that by dH dt. Now, folks, for height, I use 6, and for height, I use 18. Which one of these is dH dt? Go ahead and say it if you know. Which one of these is dH dt?
Would it be 6?
It would be 6. Why 6, Kate? How do you recognize 6 as a rate of change as opposed to 18, which is the static height when I took the picture? What's the giveaway? Go ahead.
It says it's increasing.
It says it's increasing, so I see that. And what else do I see to give me a clue? Even if I didn't see the word increasing, which you're right, though, that's a perfect giveaway, so that would perfectly work. What else? I'm looking for one other thing here. What are the units on 6? The units on 6 are feet per second. That is a rate of change. That's how you identify that goes with a derivative and not with a static value. Okay. So I'm going to take that and multiply it by 6 there, and then we're going to add to this h, which is 18 times 1/2 times dB dt, which is where we use the 4. So if we solve this now for a prime, we get, let's see here, that would be 10, we get 60 plus, that would be 36. We get 96. Folks, it would be a real bummer to have done all the math correctly to this point and to not get full credit on this problem. What do I need to include to get full credit on this problem?
The units.
The units. What are the units on this problem?
Feet per second.
Careful. We're measuring what? Area. How do you measure area? In terms of square feet. Right? Area is a square footage. Another way you could see that is, for example, right here, this 18. This 18 has the units of feet. This 1/2 is unitless. It has no units on it. It's just a constant. And then what are the units on 4? They are feet per second. Folks, what do I get when I multiply feet times feet per second? I get feet squared per second. So that's another way to see that the units in this case sort of confirm what we were wondering. So now we're looking at number 3 here. We're asked to find an antiderivative of this function. Okay. Folks, I do this problem over and over again because I find that students just aren't careful enough with these problems. You cannot take the antiderivative of the numerator and the antiderivative of the denominator. You cannot do that. Okay. What you need to do is you need to rewrite it. Now, folks, unfortunately, I was commenting on your answers, but I couldn't see your work. Okay. I am going to rewrite this antiderivative. I'm going to divide x squared into each term here. So that gives me 10x to the 4th plus 1 over x minus 1 over x squared differential x. Okay? So would everyone look at your work, even if you got the correct answer, look at your work and see if you have this step. Because I do want you guys to make sure that you're showing this step, because this is where you practice using the antiderivative symbol, the integral symbol, and you make sure that you've got the differential x on the back side. So a lot of you were missing that on your most recent exam for these problems. Okay. Now, folks, why did I do this? Well, first of all, let me ask, are there any questions on this? So why did I do this? Why did I divide x squared? Well, because now I have 3 separate terms. And we are allowed to take antiderivatives term-wise. So we're not allowed to take the antiderivative of the numerator and the denominator separately. Just like when you took the derivative, you couldn't take the derivative of the numerator and the denominator separately. But you can take antiderivatives term-wise. So now I've written this problem as 3 different terms. When we go to take the antiderivative of the first term, we're going to do 10x to the, I'll go ahead and write out the power rule just for practice. like that. What did I do? I added 1 to the exponent and divided by the new exponent to undo the product rule of differentiation. Now, this middle one is a special case, folks. The power rule does not apply to this middle term, and you could try it. If you tried to take the antiderivative of 1 over x and you mistakenly said, well, I'm going to rewrite that as x to the minus 1 dx, and then I'm going to apply the power rule to it. If you go to apply the power rule to it, what happens? You'd have x to the minus 1 plus 1 times 1 over minus 1 plus 1. What's minus 1 plus 1, folks? 0. You would get something that's undefined. So try to use the power rule on this problem. I dare you. You'll break things. Okay? Instead, which function, folks, which function when we take its derivative gives us 1 over x? The answer is the natural log of x. That is a function that when we take its derivative we get 1 over x. But the better answer and the correct answer is to put an absolute value on that. I don't really want to talk about that now, but if you would like to, come by and see me during office hours, and I'll be happy to explain that again, why we put that absolute value on there. It has to do with the domains, and that's all I'll say. Okay. This last one, by the way, I forgot to rewrite it as x to the minus 2 power, minus x to the minus 2 power. If I take the antiderivative of that, this I can use the power rule on, so let's practice that. Let's see here. That would be minus, let's do that just for fun. Folks, what did I just do there? I factored the constant negative 1 out of the antiderivative. Now I'm going to do the, oh, I don't know what I'm thinking. There, sorry about that, folks. Now I'm going to do the power rule, the reverse power rule for antidifferentiation. I'm going to take the exponent, add 1 to it, and divide by the new exponent. Okay. And when I do so, notice that I get x to the minus 1 all over minus 1, and we already had a negative, and so that's going to come out to be x to the minus 1, which is the same thing as 1 over x. Okay. So folks, jot down this work here, because I'm not going to do that work again. I'm going to do it all in my head. Okay? So I'm going to take and add 1 to the exponent, divide by the new exponent. That gives me 1 over x. And then for this whole thing, I need a what? I need a plus c. Why do I need a plus c on that, folks?
Because there could be a constant that we don't know about because it just factors out.
Yeah, and put it. I like that. I like that description, Shane. That's a better description than I was going to give. So yeah, we need to put a constant on because the function could have been plus 17, and we would have lost that information when we took the derivative, and so we can't get that information back when we take the antiderivative without giving some sort of initial condition. Okay. Additionally, just a second here. Sorry, I'm losing my train of thought. Additionally, I would like you to think of it as when you take a generic antiderivative, when you take the antiderivative, you're looking for a family of functions, all of whom have this as their derivative. And so that plus c shows you that you're talking about an entire family of functions. Great. So folks, we're looking at this Hopital's rule question. Okay? And I say to watch the chain rule on it. Because if you make a mistake, that's where you'll make a mistake often. Now, let's look at this limit. I'm going to rewrite the limit. I'm just going to rewrite it so I can point to it and talk about it. The sine of 3x minus 3x all over x cubed. Folks, the domain of this expression does not include 0, so can I apply direct substitution to it? Heck no, I cannot do direct substitution on this problem. However, if I were to think about doing direct substitution, plugging in a 0 into the numerator and the denominator, it would give me the indeterminate form 0 over 0. L'Hopital's rule says if this has either the indeterminate form 0 over 0 or infinity over infinity, you can go ahead and apply L'Hopital's rule, which may or may not make your life easier. Okay? Please, folks, a lot of times people come into my class having had some calculus and they think L'Hopital's rule's the cat's meow, or for some reason I give them the impression that L'Hopital's rule's the cat's meow. It doesn't solve all of your problems. Okay? From here on out, if I do give you a limit problem, you're welcome to apply L'Hopital's rule if it applies and if it helps you. But don't think that all problems I give you from here on out will be L'Hopital's rule questions. Okay? So, this has the indeterminate form 0 over 0, so I'm going to apply L'Hopital's rule to this. And we get the limit as x approaches 0 of cosine of 3x. Careful though, there's a chain rule, so I need to multiply by 3, minus 3, all over 3x squared. Folks, can I now evaluate this limit through direct substitution or make some other conclusion? No, I cannot. Notice that this still has the indeterminate form 0 over 0. Folks, at this point you should do a little assessment. Did we just make our lives easier? Because if you're applying L'Hopital's rule and it's not making your life any easier, then you should stop, or you should try to apply it some other way. But in this case, I think we made our life a little easier. How come? I think we made our life a little easier because the degree of the denominator got smaller and the numerator didn't get any more complicated. So that worked, so I think we should try to apply L'Hopital's rule again. If I apply L'Hopital's rule a second time, let's see here, we get minus 3 times the cosine of 3x. Oops, we got times another factor of 3, so I'll just make that minus 9, all over 6x. And I think we're getting the point here. This still has the indeterminate. Oh, this should be sine. Folks, does anyone want me to talk about that derivative? I did that. I made a mistake, and then I did it a little bit fast. Tyler, that answer looks good.
Why is it minus 9?
Yeah, what's the derivative of the cosine, Kate? The derivative of the cosine is the minus sign.
Oh, okay.
Yep. So this still has the indeterminate form 0 over 0, but I can see the light at the end of the tunnel. We apply L'Hopital's rule one more time, and we get minus 27 cosine of 3x all over 6. And now if I apply direct substitution for this, I get minus 27 over 6, which reduces to negative 9 halves.